What's up, everybody? Welcome to lecture 20 of Trig. Today we're going to be talking about section 3.4. To start off with, let's look at this definition here. So what we've got are two different vectors, u and v. We want to set u up so that it's the sum of two other vectors, called them w1 and w2. But there's a catch. We want w1 and w2 to be orthogonal to each other. That's what this symbol here means. And we want w1 to be parallel to v. Then w1 and w2 are said to be vector components, and u are said to be vector components of u, and w1 is said to be the projection of u onto v. So what does all of this mean? This definition is kind of abstract right now. So let's look at this beautiful picture right here. Thinking about submitting it to MoMA. They'll accept that, right? Yeah. Anyhow. So what we've got our two vectors, u and v. And in our picture, we can see now right away that w1 is parallel to v, and w2 is perpendicular to w1. Now, for a split second, I want y'all to imagine something. Imagine you've got a flashlight over here. You're shining it down onto u in a direction perpendicular to v. I want that flashlight held at a right angle. We can imagine you casting a shadow onto v. That's pretty straightforward. Well, if u is casting a shadow onto v, and the flashlight is held at a right angle to v, so it looks something like this, well, if that's the case, then the shadow that you cast would look like w1. This is what it means for w1 to be a projection of u onto v. We're quite literally saying, if we can compare these two things, if we can compare u and v, how much of v is like u? How much of it is in the same direction? That's kind of what we're saying here. And once we figure that out, then we need to find the other missing vector that, when added to the projection, will be equal to u. So look at what we've done, right? What we've got is this vector w1, we're adding it to w2, and it forms u. And just like that geometric interpretation we talked about the other day, when we take a vector and fit two vectors so that the tail end of one sits at the front end of the other, well, that's like adding these two vectors together. And we know that w1 plus w2 is u. Well, u is this vector right here, which we started with. So when talking about projections, what we're really doing is saying, I want this vector u, and I want this vector v. Now, I want to be able to talk about u, the parts of u that are in the direction of v. We're going to call that part of u w1. And then we're going to say, well, there's a missing chunk of u now. We're going to call that w2. But notice w2 has to be perpendicular. And this is all we're doing, right? So, okay, kind of makes some sense. How do we find it? How do we find w1? How do we find the projection of u onto v? Well, to find it, we apply the following formula here. We've got that w1 is equal to the projection of u onto v. And this thing is going to be equal to a mess. Let me be honest with you, it's a mess. This thing is equal to the dot product of u and v divided by the norm or the magnitude of v squared times v. Okay, there's a lot of moving parts here. This makes no sense algebraically yet, right? Like, what are we talking about? What is this? Well, you'll notice we can break up that denominator, right? We can break it up into the magnitude of v times the magnitude of v, which we can break up again. When we do, we get this expression down here. Well, looking at this, I don't really know what this is right off the top of my head. Like, looking at this, it's not obvious, right? Like, none of us see it right away. But that second term, this fraction here, that we do recognize. This is the unit vector of v, right? This is the unit vector in the direction of v. Okay, we're multiplying it by something. If we look, this something, isn't this just a scalar? It is, right? Because we've got u dot v, that's a scalar, divided by the magnitude of v, that's also a scalar. So this thing is a scaling factor. And what it's telling us is that we want to take something in the direction of v, a unit vector in the direction of v, and we want to stretch or shrink it by this much. So what does this tell us? This here is the relationship of how much of u, what magnitude of u, is in the direction of v. That's all it is. It's telling us the length of this shadow right here. So, as an example of a question I might ask you to find W1. And then I might ask you to find the magnitude of W1. Okay, well this is gonna suck. But not really, right? Because if you're gonna find out what W1 is, you're gonna have to apply this process. Well, this process requires you to find the unit vector in the direction of v and the magnitude by which you stretch or shrink it. So the magnitude of W1 is going to be equal to this thing right here. And this thing is just going to have a magnitude of 1 in the direction of v. That's all it is. Now, having said that, we still haven't found W2. So what are we going to do? Well, we know that u is equal to W1 plus W2. After all, W1 and W2 are the vector components of u. Well, if that's the case, then W2's just got to be whatever's missing from W1. Well, to find out what's missing from W1, why don't we just subtract W1 from u? This expression right here. What I'm saying is, if we take u and we remove W1 from it, what's left over is W2. And that's what all of this is about. I know there's a lot going on here, so we're going to go over a couple of examples. But I really want you all to stop and think about this first part here. This is the cool shit. Like, this is where math starts to happen. Upper level math, we do this in all sorts of different ways, and it's fun. Yes, math is fun. So for whoever's like, bet, all right, I'll take that bet. Math is dope. Just anyhow. I make myself laugh sometimes. I really want you all to take the time to understand what I just said here, because this is very important. If any of you are going into engineering or physics, know this. Know this now, because this is pretty much going to run, I want to say 30% of your future. Like, a huge chunk of physics and engineering is just about this stuff. This entire chapter on vectors. Huge. some of the computer science folks, you might also run into this sort of structure. But having said that, let's check out an example. All right, so for this first example, we've got these two vectors u and v. And we want to find the projection of u onto v, and we want to find two orthogonal components of u. All we know is what u and v are. So how are we going to do this? Well, we're going to start by drawing our graph. We've got u and we've got v up here. We've got the projection of u onto v. And then we have an orthogonal component of it. We have w2, right? Still hasn't answered how we're going to actually solve for these values. What we're going to do is we're going to say, all right, from just a second ago, we know that w1, the vector w1, is equal to the projection of u onto v. And we know that this is equal to u dot v divided by the magnitude of v squared times the vector v. So let's calculate these things. And let's calculate them separate so that we have everything in parts. Start off with u dot v. Well, u dot v is going to be equal to the vector 3, -5 dot the vector 6, 2. So to do this arithmetic, we've got 3 times 6 plus -5 times 2. This is going to be equal to 18 minus 10, or just 8. Okay, so the first thing we know is that our numerator is equal to 8. Now, let's find out what the magnitude of v is. Well, we can write the magnitude of v in two different ways, right? We can say that it's the square of the square root of its components, the sum of its components squared. Or we can say that it's the dot product of itself with itself. So what I'm saying is we can write it as the magnitude of v squared is equal to the square root of v1 squared plus v2 squared, the entire quantity squared. That's a pain. Or we can say that it's equal to the inner product of v with itself This is going to be equal to then v1 squared plus v2 squared, which is equal to 6 squared plus 2 squared, which is equal to 36 plus 4, or just 40. So now we know our denominator. Our denominator is equal to 40. Notice, really quickly, I want to point this out. Notice all I did here was say it's the magnitude squared. So when we write this, because we're squaring the square root, we could just drop the square root. Which is that. And these things are in fact equal. Just to reiterate something we talked about in last class. But anyhow, getting back to this problem. Now we're multiplying this fraction by v. Or rather, we're multiplying v by this fraction. Well, we know v is equal to 6, comma 2, so multiplying all of this. Notice really quickly, we can actually simplify this fraction, right? This fraction can be simplified to, what is that, 2 over 5? Right, because 4, my mistake, 1 over 5. 1 over 5, my mistake. This fraction can be reduced to just 1 over 5 because 8 is divisible by itself once, 40 is divisible by 8 5 times. So what we're going to have is 1 over 5 times 6 comma 2, which is equal to 6 over 5, comma 2 over 5. I just decided to write it here instead of over here because I was going to be crunched for space. So, we found now what W1 is. Let's write that off to the side. W1 is equal to 6 over 5, comma 2 over 5. Now, we want to find what W1 is. I mean, what W2 is. We want to find that missing part, right? Well, we know that W2 is equal to the vector u minus W1. Well, we know what W1 is, we just found that, and we know what u is. We already had that. So this all comes out to be the vector 3 comma negative 5 minus 6 over 5 comma 2 over 5 So we want to put these over shared fractions, right? We want a common denominator between these. So this is going to become 15 over 5. This is going to become negative 25 over 5. I need more room. So once we put these over the common denominator, Like I said, this becomes 15 over 5, and this becomes negative 25 over 5. And you can check my math here. If that's the case, then 15 minus 6, well, that's going to be 9. So we're going to have 9 over 5. And negative 25 minus 2 over 5, well, that means this is going to become 27 over 5. Negative 27 over 5. And that's our W2. That's our orthogonal component. Our vector component orthogonal to W1, I should say. So, W2 is equal to 9 over 5, comma, negative 27 over 5. All right, now let's say I ask you to verify that W1 and W2 are orthogonal. How are you going to do that? You're going to take the dot product of the two and see if it's equal to 0. If the dot product of two vectors is equal to 0, remember that means they're orthogonal, right? Again, that was the last lecture. So let's do that really quick. Let's check. Let's make sure that W1 and W2 are orthogonal. W1 dot W2 is equal to 6 over 5, comma, 2 over 5, dot 9 over 5, comma, negative 27 over 5, well, this is going to come out to be 6 times 9 over 25 minus 2 times negative 27 over 25 my mistake, I meant to say 6 times 9. Well, 6 times 9 is going to be 54 over 25 minus 2 times negative 27. Again, my mistake. This is supposed to be addition. We're adding the two, right? Because we're taking the dot product of them. But we're going to find that because of this negative 27, our addition becomes subtraction. So we have 54 over 25 plus negative 54 over 25, which is just equal to 54 over 25 minus 54 over 25, or 0. Now, for those who aren't sure where this 25 came from, I just went ahead and said the denominator times the denominator. So notice what we've done. We said 6 times 9, 5 times 5. 6 times 9, 5 squared. 2 times negative 27 over 5 times 5. 2 negative 27, 5 squared. And then we added them together. We got 0. So it checks out. Now we have found the projection of U onto V. That was W1. Then we found the component of U that's orthogonal to W1. That's W2, right? So that when W1 plus W2 When we add those together, we're going to get u back, and when we take the inner or the dot product of the two, we're going to get that there's 0 because they're orthogonal. Cool. So let's check out another example. So because I really want y'all to take time to absorb this material and really understand it, really focus in on it, this is going to be the last example for the lecture video. Notice though, the example is the exact same question as that previous question, right? But the vectors are different. And I wanted to do this particular example because it illustrates a problem with language that sometimes comes up. We may sometimes say that W1 and V are in the same direction, when really what we mean is they lie along the same line, they're parallel, but they point different directions. So in this case, we've got W1 and we've got V. They lie along the same line. That's pretty obvious, right? But they're pointing in opposite directions. So because of ambiguities in language and the way some people speak, the different vernaculars that we all use, it might sometimes be said that these two things are in the same direction. But again, really all we mean is they lie along the same line. Having said that, in our example, we've got the vector u, which is equal to -3 times square root of 2 over 2, comma 3 square root of 2 divided by 2. And we got the vector v, which is equal to 4, 0. Dope. Awesome. All right. So what we want to do first is find W1, right? Well, that's going to just be the projection of u onto v. We just did that in the last problem, right? So we know how to do this. The projection of u onto v, that's just equal to u dot v divided by the magnitude of v squared times the vector v. Okay, so let's go ahead and find out what u dot v is. Well, u dot v is going to be equal to negative square root of 3, or my mistake, -3 times the square root of 2 over 2 times 4 plus 3 times the square root of 2 over 2, all of that multiplied by 0. So that term just disappears. Let's go ahead and write it up here, just so we can keep tally of everything, right? So this is going to be 3 times the square root of 2 over 2 times 0. Well, this 2, the 2 in our denominator and the 4 are going to cancel. So we're going to have -3 times the square root of 2, all of that times 2, or -6 times the square root of 2. All right, so let's write this in for our numerator. -6 times the square root of 2 over 2. That is our just -6 times the square root of 2. Now, let's find out what our denominator is. Our denominator is going to be the magnitude squared of v. And the magnitude squared of v, that's going to be square root of 4 squared, right? So what I'm trying to say is it's going to be 4, 0 dot 4 comma 0. So 4 squared. Done. 16. All right, so this is going to be 16. Well, all that's left now is multiply it by v. Fair enough. V is just 4 comma 0. Well, notice that we've got some reductions going on in here, right? We could divide, we could pull out a 2 from our numerator and our denominator. When we do that, we're going to end up with negative 3 square root of 2 over 4, my mistake, over 8 times 4 comma 0. And when we multiply this fraction all the way through, what we're going to end up with is negative 3 square root of 2 over 2 comma 0. Wait a minute. It's just the x component of our original vector. That's all W1 is? It's just the x component? Well, let's look at what we've got here. V lies along the x-axis. So any vector parallel to it, it's just going to be an x component, right? So W1 necessarily has to be just the x component of u. That means then the remaining component is just going to be the y component. So what I'm saying is we just found that W1 is equal to negative 3 square root of 2 over 2 comma 0. And when we subtract that from u, we're going to get just the y component. So W2 is equal to u minus W1. This is equal to negative 3 times the square root of 2 over 2 comma 3 times the square root of 2 over 2 minus negative 3 square root of 2 over 2 comma 0. And this, well, this is going to be equal to 0 comma 3 times the square root of 2 over 2. And if we wanted to check, we could check to see if these two vectors are orthogonal to each other. Which, hey, they definitely are, right? Because we have a 0 in the x component of W2, and we have a 0 in the y component of W1. So it just comes out to be 0 plus 0. So the dot product is 0. So they're definitely orthogonal. Really, this is all we're going to be doing here. In the next lecture, we're going to be talking about work, as in physics, the work done by some force, and that's going to be using the projection and the dot product. So If you are at all uncomfortable with this, please reach out and let me know. I'll be happy to help. But in the meantime, have a good one, everybody.